Okay, continuing on with that proof. Sorry about the awkward interruption. Little incident. Okay, so we have the T AQ transpose written in this form, the AQ T transpose written in that form. We know the rank of A transpose A equals the rank of this stuff here, our asterisk equation. So we'll use these versions of these matrices to fiddle around with this, ultimately getting out R. I want to get out the rank of matrix A. Okay. As I said, we've got these two products of matrices here represented like this. So do the matrix product, the way you multiply partition matrices, gives us an A1 transpose A1 up here. The beauty of this is A1 is a full rank. We collected together all the rank of A in a certain sense in that matrix A1. So by the start equation, the rank of A transpose A is the same as the rank of this, which is the same as the rank of this. The rank of this partition matrix, think of it in terms of dimension of the column space. There are no contribution by columns over here with the zeros. So the rank of this matrix is determined by the columns of the first part. No contribution by the zeros added down below either. So the rank of this partition matrix is A1 transpose times A1, but A1 is a full column rank. It was full column rank R. We collected all the rankness of matrix A into this little A1 matrix. Part 5 told us that if A1 is a full rank, then A1 transpose A1, the Gramian product, is a full rank. Full column rank matrix will produce a Gramian product that's full rank. Let's take a look at that. Part 5, A transpose A is a full rank if and only if A is a full column rank. It's exactly what we have. We have A1 as a full column rank. Right, A1 is a full column rank. So A1 transpose times A1 is a full column rank as well. That rank must be R. So we've shown the rank of A transpose A equals R. And R is the rank of A. And there you go. The rank of A transpose A equals the rank of A. That was the claim. Back to the notes. Okay, that finishes up this A transpose A stuff, this Gramian product stuff. We just used theorem 3.3.5 extensively to show the rank of a product is less than or equal to the minimum of the ranks was the result. So this gives us an upper bound on the rank of a product. The following gives us, in a sense, a lower bound on the rank of a product. So here, it's called Sylvester's law of nullity. If A is a square n by n matrix, and B is an n by L matrix, so the product AB exists, the dimensions are appropriate for that, then the rank of the product is greater than or equal the rank of A plus the rank of B minus parameter n. So let's go through the proof of that. All right. So let R be the rank of A by theorem 3.3.9. As we've done before, you know there's matrices P and Q, products of elementary matrices, that allows us to basically elementary row and column operation, create this what we call full rank equivalent representation or something like that. We can create a R by R identity matrix up here, like we did in the previous proof, permuting the rows and permuting the columns and doing some row reduction. Define matrix C to be the inverse of this, product of elementary matrices, invertible. Define it to be P inverse times this partition matrix times Q inverse, because I said so. So we'll see it work out in the arithmetic. Then if we take A plus C, all right, we're not really looking at sums of matrices, but it'll come out in the computations. A plus C, matrix A, is, well, we could solve for it with P inverse and Q inverses, moving those over. So there's what we get for matrix A. Matrix C, by definition, is this. Okay, I was worried about having a sum, but it's about to go away. We could factor a P inverse out one side, a Q inverse out the other, left and right. Then we get this matrix added to this matrix. Well, that'll just together produce an identity matrix, I sub n. So we've got an identity matrix here. We can absorb that in one or the other of these inverse matrices. And so we get A plus C equals P inverse Q inverse. P inverse and Q inverse are full rank, and they're invertible matrices. They're n by n matrices. So the rank of C equals the rank of P inverse matrix Q inverse. Theorem 3.311 says if I take a matrix and multiply it on the left by a full rank matrix, that doesn't change the rank of the matrix. If I multiply it on the right by a full rank matrix, that doesn't change the rank of the matrix. So we can conclude that the rank of C is the same as the rank of this, Theorem 3.3.11. Rank of this is easy. Got a little identity matrix down here. Think in terms of rows or columns. We'll get an n minus r out. That is, we'll get an n minus the rank of A out. We got into this by letting r equal the rank of A. Okay, so we got the rank of C is n minus rank of A. That's somewhat close to a piece of this. All right, so if we take an n by L matrix B, rank of B, let's apply those same permutations to it. P inverse, Q inverse, as we're applying them to the left to this B. All right, full rank matrix here with a P inverse, Q inverse stuff, so the rank doesn't change, Theorem 11. P inverse, Q inverse we had as A plus C. So we can replace this with an A plus C and distribute to get the rank of AB plus CB. Okay. Rank of the sum is less than or equal to the sum of the ranks. Theorem 3.3.6. Let's run and look that up. That's in this section. 3.3.6 told us 3.3.6, huge section. There it is. Yeah, rank of the sum is less than or equal to the sum of the ranks. It's a little bit more than that, but that's the part we need. So back to the proof. So that inequality is established. We know that the rank, say, of CB is less than or equal to the rank of C. It's also less than or equal to the rank of B, that minimum thing. That one I remember because we've used it a bunch. So we can make this claim here. And we saw on a previous slide that the rank of C was n minus r, n minus the rank of A, and there it is. So rank of B, less than or equal to rank of AB plus n minus rank A. Let's keep the rank AB on the big side and move this to the other side. We'll have rank of A plus rank of B minus n, less than or equal to the rank of AB. And that was the claim. Okay, so back to that part of the notes, thankfully near the end. Okay, so there's Sylvester's law of nullity. We haven't actually defined nullity just yet, but we'll get there. We'll talk systems of equations and null spaces here one of these days. The following result, totally unsurprising. In fact, if you remember very much about sophomore linear algebra, maybe beyond systems of equations, you ought to remember this. An n by n matrix A is invertible if and only if its determinant is non-zero. All right, so let's peek at a proof of that. This goes back a ways, we've built up a fair body of knowledge here. First off, we know Theorem 3.2.4, determinant of the product is a product of the determinants. So if A inverse exists, then we could say the determinant of the identity equals the determinant of A times the determinant of A inverse. Determinant of the identity is 1. So we'd have determinant of A is 1 divided by determinant of A inverse. All right. Well, that's not 0. So the determinant of A is not 0. If A inverse exists, then the determinant of A is non-zero. Fairly easy from this little formula. The other half, I need to appeal to a couple of sections ago, Theorem 3.1.3. We expressed A inverse in terms of determinants and adjoints of a matrix. Remember that? We did it. So if the determinant of A is non-zero, then we can use this formula. Adjoint of A was just computations of a bunch of determinants of minors. I don't have any trouble with that matrix existing. We can take the 1 over determinant of A, and this gives us a formula for A inverse. So with the body of knowledge that we have, that's quite easy. We had dealt with determinants. We had never linked together determinants and inverses, except for that little adjoint formula that we had, as cleanly as this. But we can now say this type of result right here, and that's totally consistent with what you do in sophomore linear algebra. Also, it is a result that makes so much of the eigenvector finding and the eigenvalue finding work. When you set up, say, systems of equations to find eigenvectors. This idea here is totally how it works. Remember, you take determinants of things to find eigenvalues. Determinant of A minus lambda I is how you find the eigenvalues, intimately related to this. Okay. Gentle makes a comment concerning some applications of the following. Gentle motivates finding inverses of sums and differences of matrices, A plus B inverse, A inverse plus B inverse type things, by referring to regression analysis and the adding or the omitting of data. I'll leave it to you to read through page 93 on its motivation. But we make the following claims, which are left as an exercise. Probably don't think I even want to read all of them. Claim is A times I plus A inverse is I plus A inverse inverse, and so forth. There's some transposes in here. We've got some matrix addition. Might look at, how about this one? How would you prove this? The claim is the inverse of matrix A inverse plus B inverse, the inverse of that matrix in parentheses, is this thing here. How would you establish that? Well, I don't want to find the inverses. I know they're there because I know we're dealing with full rank matrices. I guess I could just take this matrix and multiply it by this thing and see if we get the identity. That'd show their inverses. I only have to do it on one side too, if I quote the appropriate theory from our past. So these are very computational. You know properties of matrix multiplication, distribution, and so forth. You know how inverses interact with products, similar to the way transposes do when you're dealing with invertible matrices. So this bunch of 7 alleged identities, no problem. Straightforward computational proofs of those left as an exercise. We've said a lot of stuff about invertibility, and we're making the assumption that you know, everything that's got an inverse sign on it actually is invertible, which it might not be with just the straight up idea that A and B are themselves invertible. For example, B could be negative A, and we're going to have some problems with the zero matrix here. But we're assuming none of that kind of thing happens. One last result in terms of these Kronecker products. Okay, we did very minimal stuff with Kronecker products, I think. But let's go through proof of this. It's a nice behavior of Kronecker products. It says let A and B be n by n full rank matrices. Then the Kronecker product satisfies. The inverse of the Kronecker product of A and B is the Kronecker product of A inverse with B inverse. All right, our last proof from this lengthy section, and it's not complicated. You need to remember how you multiply with the Kronecker product. Okay, so let A and B be full rank, so A inverse and B inverse exist. Let the entries of matrix A be A sub ij, and let the entries of matrix A inverse be C sub ij. Here's one. We're going to consider the Kronecker product of A and B, and basically here's the definition. So what you do is you take all the entries of matrix A and multiply each of them by matrix B. That's how we did Kronecker products. So I need to know the entries of the first matrix to write this out. That's why I say let the entries of A inverse be given by the C sub ij's, because it's the first matrix in a Kronecker product. Also, between these, we've taken a regular old Cayley product, a regular old-fashioned matrix product between them. That's the setting in which you talk about inverses. So we want to show this equals the identity. Okay, so here's a Kronecker product of A and B. Here's the Kronecker product of A inverse and B inverse. It's the entries of A inverse, each of them with a B inverse matrix, all multiplied on the right. Okay, so we've got effectively a partition matrix, and we want to do our row times column stuff. So we'll take the ith row times the jth column. That'll give us A sub I k, will range from k equals 1 to n, times B. Each of these will carry a matrix B along with them. And then we'll do C sub kj, and each of those will carry a B inverse along with them. Well, the B and the B inverse are going to get together to produce appropriate sized identity matrices. A and B are n by n. That identity will be n by n. So what we end up with is sum from 1 to n, A sub ik, C sub kj. Sounds familiar. It's picked up this n by n identity matrix and the weird Kronecker stuff that's going on. But that's what we get for the Kronecker product. And look what you got here. We've got ones along the diagonal from all of these identity matrices. So what we're getting is some sort of weird partition matrix with a bunch of identity matrices. And so, since we're getting those identity matrices, we're getting lots of zeros. The only time we ain't getting zeros is when when let me think, when I equals j. Yeah, when I equals j is the only time we're not getting zeros out in these matrices. But we're getting sums. Actually, let me reword that. Let's bring this, bring that I sub n out. Not quite, because I could bring it out. We're dealing with a partition matrix. I'm looking in the wrong place. I want to compare this A sub ik with a C sub kj. Remember the C's, they're entries of the inverse matrix. I want to concentrate on the summation here. What happens when I sum from 1 to n of A sub ik times C sub kj? That's where I should be looking, sorry. Well, the C's are entries in the inverse matrix, so when we sum these up, we're getting 0 out unless I and j are the same, in which case we get 1 out. That's how we get the ones along the diagonal, then applied to these identity matrices. So what we get is a big giant identity matrix, an n squared by n squared identity matrix. So we multiplied these two matrices together. We got an identity matrix out. They are inverses of each other. So the proof of that, it's actually similar to the way I talked about proving all this stuff. Only this time we had to deal with the burden of a Kronecker product. And that's the material of section 3.2. Let me make a little synopsis on the vocabulary that we've introduced here to show you that what we've said here, even though it didn't maybe originally look like what you saw in linear algebra, it really is what you saw in linear algebra. So to summarize our vocabulary, here's what we have. A inverse first, A inverse exists, then A must be a square matrix. We only invert in square matrices. Square n by n matrix A is a full rank if the rank equals n. And this value is the dimension of both the row space and the column space. We can say, we stated that as theorem 3.3.2. So we showed dimension of row space equals dimension of column space, something you probably don't do in linear algebra, but you use. A full rank square matrix is non-singular. That was our definition of non-singular. We saw later that such a matrix has an inverse. So non-singular means invertible. Singular matrices are bad by definition. They're rank deficient square matrices, and they're not invertible. So same vocabulary as sophomore linear algebra. Non-singular matrix is invertible. And finally, in this last result, we showed, or one of these last results, we showed that A is invertible if and only if the determinant is non-zero. And I promise you, we'll use that a whole bunch in the section on eigenvalues. When we start doing eigenvalues and eigenvectors, this determinant property will pop up again and again. Theorem 3.3.16 will be our best friend in section, I think it's 3.7 or 3.8. And that's the content of section 3.3. The following few sections aren't nearly as gigantic as these first three in this chapter, but chapter 3's got the bulk of the material. I will see you in section 3.4, and I promise you it won't take this many hours to get through 3.4. Have a nice day.